Hello and welcome to the Cyber1 YouTube channel. My name is Ray, and in this video, Spot Micro Part 24, I'm going to do an update. Okay, so in the last video I did mention that I was looking at changing the program to support the My Robot Lab configs. So if we go to the Runtime tab up here, we can see that we've got configurations. So this is the same place where we would normally start a service. We can actually start a service still with this, but we can go to the spot in the configuration and we can actually save this configuration. Comes up quite happily and we hit save. And it saves out all the configuration as we're currently using it. Now this is handy that in as much as we can change the settings for each of the servos in the robot, and then when we're happy with all of our servo positionings, our limits, we can save the config and it will remember it through the config. We don't have to then go into any Python code and edit the Python code to change our configuration. Now the way we do this is with a different set of programming. So I'm actually going to connect to the Raspberry Pi built into Spot using VNC. So what we're looking at now is a VNC display. And I'm actually looking, if I'm running My Robot Lab version 1.1.1041. It is not currently the latest version. I think they're up to 1.1.1054 at the time of this recording. It might even have gone on past that one since I started recording. All right, so if we have a look in My Robot Lab, we have this folder called Data. And inside Data, this is where all of the user data is stored. So there will be a set of configurations, default configurations and programs and the like, that's part of the resource folder. When I get these GitHub structured correctly, there'll be another one called Spot that we can then copy in somewhere. It may even eventually get integrated into the resource. In any case, any programs that we want to create, we need to put into the data. So I've created a folder here called Spot, and that's where all of the programs that I'm writing will be going into. One of the default things in My Robot Lab is config. So if we go into the config, we'll see that we've got the default config. This is one I created while I was experimenting, which is the Web GUI config. And then we have the Spot config. So if I go into the Spot config, we've got all these YML or YAML files. Now the very first one that's going to run is called Runtime. So if we start Spot with the command line /myrobot_lab -c spot, using a capital S in this case, and press enter on that, it will actually start using the config. So things that would normally be started in the order they're started won't be started that way. It'll default to whatever's in this configuration instead. So let's have a look at the runtime configuration as a text file. So the first line basically describes what it is. Auto start peers is true, enable CLI is true, and locale, I'm in Australia, so I'm using the ENAU locale. Log level null, and registry is the one that I'm really interested in here. So the registry is a list of all of the services that will be running by runtime. Remember, runtime is the one that starts and stops all services in My Robot Lab. It's the top level, so to speak. So it's always going to start itself first. There's another one called security, and that's where it stores keys and things like that used on some sites that require them. Web GUI is to do with the web server that My Robot Lab runs. And we can connect to that web server with a web browser. typically Chrome or Firefox for that matter, from another computer if we want to, or from on the Raspberry Pi. More on that when I look at the WebGUI service configuration. Intro. Now this one is an optional one. I've left it on there for now because it's handy for the intro page on the because it runs on the web interface. Raspberry Pi, so we are running this on a Raspberry Pi, so we are starting the Raspberry Pi service. The back and front of both the PCA 9685s. The MPU 6050A is the inertial measurement unit, which is located at the back here, and it's got a little green light on it. The LCD PCF8574 is located in the back of the robot here, and that's actually a PCF8574 that's mounted to the back of the LCD unit, which is a 16 character by 2-line unit, and that runs the LCD service, which is connected to that below it. And that's the HD 44780 service. Then we have our servos, all 12 of them. We have our clock service, which is used to mostly update the LCD service. And then finally, we start Python. Now, if you start My Robot Lab normally, without specifying to use a spot config, it will actually start Python just before intro. In this case, I want Python to run a script on startup, but I want that script to run after all the other services are created first. And we'll come to that as well. The type for this service is runtime, and virtual is false because we're running it on real hardware, not a virtual machine. So let's close that out and we'll look at WebGUI. Now, WebGUI in this case, auto start browser I have set as false. Now the default for My Robot Lab is set to true. So when you start My Robot Lab on the computer, it will launch the Chrome web browser. In the case of Raspberry Pi, the Chromium web browser on that machine. The Raspberry Pi is not an overly powerful computer, and Chromium does actually suck quite a few resources. So ideally, we don't want to run it on the Raspberry Pi, not when we can access it through another computer. And I do that with my more powerful Windows computer. So by default, I don't start the web browser on that computer. We do start any other peers, and the default port is 8888. So we can change the port that we connect to this on. So if you're worried about security and people getting in and hacking into your robot, you can change what port number it's on, which makes it a little more difficult to get into the robot if you don't know that information. Okay, so the Raspberry Pi service, there's not much to it. It's a type Raspberry Pi, auto starts peers. That's it at this stage. The MPU 6050, we start this up on bus 1 connected to the Raspberry Pi, and its address is 0x68. So all this information is in here. It auto starts. So originally the default process would not auto start the MPU 6050 service. It would start the service but wouldn't run it. This command here on line 7 actually starts it running, and that's important later on. Okay, so in the case of our PCA 9685, it uses the Adafruit 16C servo driver, which is listed here. That's the name of the service. We're on device 1 connected to a Raspberry Pi with address 0x40. If we have a look at the front one, it's 0x41. Again, we auto start peers. Servos are pretty much a standard thing, so I'm just going to take one as an example. So in this case, I've I'm looking at BL, which is the back left wrist. You can see auto disable is true, auto start peers is true. Clip, I don't know what that one does at this stage. Controller is back. Enabled is false. As far as I know, it should be true. Idle timeout is 3000 milliseconds. Inverted in this case is false. Some of our servos, in fact half our servos, are actually set to true. Our max in, our max out. So the two ins, the max and the min in, are the input range for the servo service, and the min and max out are the output range. So this is a mapping function, and we use the output range to set the limit so that the servos won't physically go past the end of their travel. Now they use degrees in these settings, and that's not strictly correct. They probably should have used microseconds, which is what the pulse width is, but there's been arguments on that back and forth over many years. I've seen those arguments running for over 6 years. At the moment they are still in degrees, which doesn't necessarily correspond to some servos. For example, the Arco servos are 270 degree outputs. So the 0 to 180 doesn't quite match up with these. Incidentally, 0 on this is 0 degrees on these, but 180 actually equals 270. All right. The pin number that we're connected to on the PCA 9685 is pin 10. We've got our rest position, we've got a speed setting. We're not using the sweep. We can turn that on at a later date if we want to, but I can't see any reason why we would for this build. Synced is null because we're not syncing it to any other servos. And of course, its type is servo. This has slightly different numbers for each of the different servos, based on the individual servo configuration. Now, the last one that starts up, there is a clock service here somewhere. Here we go, clock service. It's set for a 1000 millisecond interval. We start it running, which is pretty much all that we need for that one. So when my Robot Lab starts up, it starts the clock service, it's running, and it gives a tick every 1 second. And I've actually got a routine that captures that and then updates the display for the LCD. Then we have this important one called Python. And I started after all the other services running because we run the start scripts data spot start pi. Now there is stop scripts, so we can actually run our own scripts for when we're shutting down. So if we hit the power button on the web interface, it'll start the process of shutting down the robot, and we can actually have it call a stop script. So we can, for example, tell the robot to go into a rest position and power down the servos, and then it turns off everything else. So we make sure the robot is in a stop state before, like a safe state to stop before we actually turn it off. And that's something that we'll have to add in down the track. So there is a copy of my YAML files up on the GitHub, so you can copy those, copy them, complete spot into config, and when you run the config for spot, it will run those. Now in Python, it did say data spot, so minimize that, so data spot, and then it runs start.py, and that's this one here. So let's open that one up. I'm going to open it up in a text editor. So you may have noticed this is all running on the Raspberry Pi itself. So in my program, and this one's noted as version 0.2, the previous one was version 0.1. This is designed to run on Nixie from about version 1000 onwards. The running folder is data spot. The robot's name, while I'm not using it yet, I may use it for speech recognition down the track, and that will be a keyword used in that. Now I've commented out the common variables.py. At the moment I'm not using them. In the original version there was a lot of configuration done in there as well that was fairly common, and at this point in time I'm not using them. It did have the setup for the finite state machine that was being created within Python. There is actually a service for finite state machine now. I still got to learn to use it, but I am planning on using it because it will control things like going in and out of the rest position. But for now, we don't need to use common variables. Now, we've already started, as part of the startup sequence of my robot lab, the back PCA 9685, but I did find that there is some variations within these devices. So the clock that is used to control this entire chip is based on that little black chip in there, and there is variations from board to board or batch to batch. So one of the things I found when I was analysing and trying to find some bugs I had in the system, the PWM width, my robot lab by default has set to 60 Hertz. However, when I was testing mine, I was getting closer to 70 Hertz as the PWM frequency. That meant that all of my center positions on the servos were a little bit out. And I found that by changing this PWM frequency down to 54, actually brought the centers back to closer to zero, or back to closer to center, where they should have been. This may be different for different boards when you're building, so it is something that you need to tune manually, and I would not change. The default is 60. I wouldn't go any more than one step at a time. When this changes, it changes rapidly. After you execute this with a different value, moving your servos will give you an idea as to what's going on. And it can be quite dramatic. Okay, so the next part, I've created a Python class called foot class. And this then runs that foot class and creates all of the background program required to manipulate and run the legs. That routine has all of the kinematics, both forward and inverse kinematics, built into it. So if you go back through earlier videos on this subject, I think videos 10 onwards, I do go into a lot of detail on how the forward and inverse kinematics work, and I've basically taken all of that and put it into the foot class routines so that I'm not having to repeat code repetitively for each foot. The next line 55 and 56, line 55 actually starts the class and it calls it legs. So we end up with our legs is equal to feet, which is the class to call in multiple legs, multiple foots, and we pass into that a link to the object for each of our servos so that it can actually directly access them. So there's actually 12 parameters being passed. At this point in time, I'm also disabling the auto level, and I think by default it's disabled on startup, but just to be on the safe side, I'm actually issuing the command anyway. Now, one of the other reasons we need to make sure the MPU 6050 was actually running in the config section is if it's not running, then this statement here is not true and none of this gets run. And this routine here forces the MPU, or loads the factory trim for the gyroscopes into the MPU 6050. I'd been having a lot of issues where the X gyro would be showing like -2 or -3 all the time. That was throwing out the roll and pitch. and your features coming off the inertial measurement. By applying the factory trim, the test factory trim, it actually cancels it all back to zero for me. I then create a method called update orientation and passing data. The data contains the pitch, roll and yaw coming from the inertial measurement unit. So every time there's an update, this little routine gets called, and then I then pass all of that to the legs update IMU data. And that's another feature that's in there that will update it to make sure the robot is getting a continual update of the inertial measurement unit. The default setting is 3 Hertz, so that's 3 times a second. So we're actually updating the inertial or the foot reference every 3 seconds. And that's important when the auto level is turned on. This command here, Python subscribe MPU 6050, publish orientation, Python, and then the name of this function just here is the one that actually puts that link in for the callback, so that the inertial measurement unit, the MPU 6050, will call that routine all the time. I'm not using the LivePi anymore. That's the one where I had all of the forward and inverse kinematics previously and the leg speed controls. I honestly haven't got any leg speed controls in there at the moment, and I'm not sure that I will need them at this stage. We'll find that out later on. I've still got a fair bit to do with the program updates. I am planning on creating a heap of gestures called gestures in gestures.py, but at the moment I'm not running any. On account I haven't really got them working with the foot class yet. So we'll close that off. And the one that's important here is foot class. So in foot class, again, this is version 0.2. There was a change that was found. This here should actually be a capital F. I'll fix that while I'm in here. There was actually a chat GPT that found that one today. Other than that, most of this is okay, according to it. So the very first, there is a class called coordinates, and all it is a storage vessel for our coordinate system. We have the servo class. The servo class is for each individual servo. It actually links to it and gives us access directly to the functions of the servo service. So we get the minimum, the maximum and the rest positions. We can also get the current target position and the current position. So we can actually tell it where to move to. I've also got, just recently added, turning the auto disable on and off. That's one of those ones where you don't necessarily want it to auto disable all the time. So when the robot is standing, you don't want it to auto disable the servos because it will fall over. But when we go down into a rest position, then there's very little load on the servos and we can actually turn them off quite safely and the robot won't fall over. So I needed to have those routines in there. Next is the foot class, and it's actually a combination of 3 servos: the shoulder, the arm and the wrist. And it actually also has information on there on which of the 4 legs it is. It is possible that we could extend this by adding in center left and center right and make a hexapod, or adding multiple centers, making as many legs as we want. So we could make a centipede type robot. I haven't thought about doing that at this stage. We do pass in, however, a lot of useful information, or not so much pass in, but we have built into it by default the length between the foot and the joint for the arms, We've got the length between the center of the robot and the shoulders, both in the X and the Y axis. We've got the length between the foot and the wrist. So there's a lot of information there that we require, mostly for the kinematics. Now, when it comes to the kinematics, we have two types of planes of reference that we use on a regular basis. We have the robot's plane of reference. And if I actually come all the way down to, I have actually gone over most of this in the past, so I'm not going to go over how all of the kinematics work, but I am interested in this class of feet, which has 4 feet in it, obviously. So we define the 4 foots, and we can actually access and get the information on the roll, pitch and yaw. Now we can actually update this and move the robot around as a result, turning the auto level on and off, making the robot go up and down. We can also control individual feet through the leg class. Now what I want to do is get into our robot itself. So come back to here. If we go to Python, you can see I've got this script started. That's actually called by Python, so therefore it's listed in there. But if I go to legs and I go print legs and then execute that, down the bottom it'll actually give us a full status of where every leg is in the robot at the moment. Now, I haven't got the calibration of these servos correct yet. I've got a fair bit of work I need to do to get them correct. I think when I do, it'll be reflected in here as well, and I'll save my config and I'll upload my config to GitHub, so if you want you can download it, but you will most likely have to do your own configuration for each servo. In order to get this configuration right, I am getting an inclinometer. So it's one that will tell me the angle that the leg is relative to gravity. Then I'll be able to use that to set all of my servo input positions to match my servo output positions, so to speak, in the real world. Now, one of the things it does show us, it shows us all of the servo positions, so the shoulder, the arm, and the wrist, and we've got that for each of the 4 legs. It also shows us where the foot is relative to the robot plane of reference, and that's X, Y, and Z coordinates. So in the case of the back right foot, this one here, it'll have a positive X. I would have thought it would have had a negative Y, but this is saying a positive Y, and it'll have a negative Z, so the feet are below the center of the rope. And according to this, the feet are actually forward of the center, so there is some error in my servo positions. When you look at the front feet, Y 185, so from the center of the robot 185 forward, it probably is close to that, and you can see all of our Z readings. Now the ICOMPOR is the inertial center of mass plane of reference, and that is where the feet are in relation to the ground if the robot was pointing. Like if your line for Z-axis is straight down through using gravity, it's where your feet are relative to that point. And it will be slightly different. So if the robot was sitting dead level, dead flat, in theory, these two values should be very much the same. And if you look through them all, they are very similar. The differences is in the pitch, roll, and yaw. If we look at the MPU 6050, we can actually get our pitch, roll, and yaw. So there's a little bit of error there. If I move the robot around, just rocking it slightly, you can see the little display moving around. Incidentally, if you're running this on Chromium, on the Raspberry Pi, this graphic doesn't work, but it does work quite well running on a Windows computer. So that's where I'm up to at this point in time. All these files have been loaded up to the GitHub. If you like these videos, don't forget to click on like, subscribe, and ring that notification bell. This is a form of support that helps the channel a great deal and costs you absolutely nothing. If you'd like to support the channel further, I do have a Patreon, and you can join my long-term patrons, MRL45, and my VIP, Go Lucky, in supporting the channel. They've been supporters for 18 months now. I also have a Discord channel, or Discord server I should say, and there is a channel in that server specifically for Spot Micro. The links for the Patreon and the Discord are in the description, and we'll see you in the next video.